Oops. You ready to go whenever?
Mm-hmm.
All right, give me a B. Give me an F. Give me an S. Give me another S. Henry's going to tell us more about it.
All right. Thanks for the warm-up. Sorry. All right, thanks for the warm-up. So last time we discussed the decoupling limit of BFSS, or the de-zero brane quantum mechanics. Right, so the conclusion was that we sort of have two pictures, right? One is the near horizon region here, and another one is just the 0+1D super Yang mills. Okay, so these two pictures have to be equal, and there's also some sort of flat space region on the outside, but they're the same in both pictures. So it's natural to identify, this near horizon region with the 0+1D super Yang mills. Now I've drawn this in a little bit more detail than I did yesterday. So here I'm drawing half of the thermal circle, which was used to produce the Lorentzian evolutions here. Right. So if you like, this is the thermophile double, right? This is e to the minus beta h over 2. This is the Euclidean portion that I've drawn here. And I've also not just considered the pure thermophile double, but I've also considered some insertions, let's say on the boundary of the Euclidean path integral. Right? So one insertion could be somewhere here. And the bulk picture is that it creates some excitation that lives in the near horizon region. And in both cases, we argued that the energy of this excitation in the decoupling limit survives. Right? So it's a very tiny energy. So it's, in principle, it could be a large energy as measured in the bulk. But when you account for this redshift factor, it becomes an energy that scales like g to the 1/3 power. So that survives the decoupling limit. Okay. So the conclusion is that any sort of excitation that you put inside the bulk here, whether it's a massless mode, a massive mode, in principle something more complicated like like some D brane, for example, it will survive the decoupling limit. And we should have a holographic duality which relates this non-perturbative Hilbert space of quantum gravity excitations to some boundary system. Yeah. Okay. Yes.
Can I understand the blue curve on the right-hand side as living on the boundary region of your near?
Yes, roughly speaking. Yes. Okay. Yes. Yes. So there's a region where this warp factor, which I've simplified in the decoupling limit to just be rho to some power, right? There's a region in which that decoupling factor, where the two terms in that warp factor are roughly comparable, and that sort of defines the boundary here. And if you're sort of in the low energy limit with the GS goes to 0, you can actually just think of the quantum mechanics as sort of living at that region. It's really at infinity, though, in the Penrose diagram that we drew yesterday, right? So.
Plus a sphere of 8-dimensional factor? A factor of 8-dimensional sphere?
Yeah, so the 8-dimensional sphere is not explicit in the boundary description, right? So somehow the entire dynamics of the matrices, they build up the 8-dimensional sphere that forms the horizon. So the 8-dimensional sphere is a little bit analogous to the 5-dimensional sphere in ADS5 times S5. Okay, so I think that's another kind of a, well, if you like, a general feature of holography that we would like to understand better in general. So, right, so how do we understand the emergence of not just ADS space, but some internal dimensions, et cetera? Okay, so I've written the metric in the decoupling coordinates. I've also performed a very simple change of coordinates to the z coordinates where z is related to rho in some simple way. And we get the following metric in z coordinates. Okay, And the cool thing about the z-coordinates is it looks very much like the ADS coordinates, right? So this factor just looks like ADS. And in principle, well, if we had a finite temperature, we would also have these F factors from this metric here. So this whole factor here looks like either vacuum ADS or the Poincare ADS, or it looks like the ADS blackbrane if we have these warp factors F. Okay? So the curious thing, though, is that the ADS blackbrane has an F factor which is not exactly the F factor that you might naively guess, right? So in particular, this D is a non-integer. So it kind of looks like an ADS blackbrane in some fractional number of dimensions. Okay, so I would like to explain that a little bit more. Okay. Yes. Another thing, okay, so that's going to be part one of the lecture today, is going to be understanding the decoupling argument a little bit better. So we're going to discuss not just the decoupling of the geometry, but also some correlation functions in the matrix model. Right? How do we get that from the decoupling argument? What is the relationship to this fractional dimensional ADS? And part two, we're going to start discussing scattering in the matrix model. And that will be more directly related to the original BFSS conjecture. OK, but before I did that, I just realized yesterday I probably said it a little bit fast. In case you haven't heard about M-theory, I thought I would spend just 30 seconds on this one lightning-fast review. So M-theory, right, as I said yesterday, is an 11-dimensional theory. And it has basically one scale, which is the Planck scale. Okay? If we compactify it on a circle of radius r, and that circle is small, we should get type 2a. So these are some of the things that we suspect based on many, many conjectures. And you can ask what is the relationship between the two M-theory parameters, R and L Planck, with the type 2a parameters, which are alpha prime and G string, right? So what is the logic? How do you connect those two parameters? Well, there's one equation which we talked about yesterday. So yesterday we discussed the mass of a d0 brane. So if we have n d0 branes, from the M-theory point of view, we think of that as some Kaluza-Klein graviton in the compact dimension, right? And the mass will be n over r. So n is the Kaluza-Klein number. In the d0 language, it is the number of d0 branes. Okay. And then we know from type 2a string theory that the mass of a d0 brane goes like 1 over g string in string units. Okay. So on the other hand, the Kaluza-Klein momentum goes like 1 over r. So that identifies that's one relation between the circle r and g string times L string. Okay. Another relation comes from thinking about M2 branes. Okay. So the only thing you need to know about M2 branes is that there's something with a 3-dimensional world volume. Okay. And since there's only one scale in M theory, it's natural to think that their tension goes like 1 over L Planck cubed, right? Because there's a 3-dimensional world volume. Right. That's the only dimensional scale. And if we wrap an M2 brane now on the compact circle, right, then we'll get some 2-dimensional object from the 10-dimensional point of view, right? So that will be a string, okay? And that string, so what will be the tension of that string? Well, from the M-theory point of view, it's 1 over L Planck cubed times the radius of the circle, right? We're reducing on that circle. There's some energy. It should be this times r. And on the other hand, from type 2a string theory, it's just alpha prime, which is 1 over L string squared, right? So this relation fixes the dependence of r and L Planck and the alpha prime and GS, either in type 2a or in 11-dimensional units. I should also say that from the boundary point of view, we have this G squared Yang-Mills, which, as I said yesterday, has some units, right? And that's related to the fact that the Yang-Mills theory has a relevant perturbation, right? So the fact that it has a relevant perturbation, the fact that the Yang-Mills interaction is relevant means that this coupling constant has units of 1 over L string cubed in the denominator, and it's related to G string this way. So we could express G squared n either in terms of the type 2a parameters or in terms of the M-theory parameters using these two relations. Yes?
M-theory, do you have to put it on a background with the circle, or is it just to relate it to string theory?
It's just to relate it to type 2a string theory. Yeah, in principle, you have many other backgrounds. Okay. So for example, you could consider on a torus, then it would be related to type 2b and so forth. OK, so this was just the lightning-fast review of M-theory, in case it wasn't super clear yesterday. OK, now let's go back to the decoupling argument. OK, so I want to just make one small variation of the decoupling argument, which is the following. So in this particular picture, right, we could have had some flat space excitation, right? And a slight variation of the decoupling argument is not to consider perfectly flat space, but to consider flat space with some graviton, some, let's say, linearized gravitational wave in that background, okay? Then we can rerun the decoupling arguments, and we'll get another duality, right? Of course, it's exactly related to the original duality in the limit where the the amplitude goes to 0, right? So what happens when we think about that argument? Okay, well, from the point of view of let's take the point of view of the 0 plus 1 dimensional super Yang-Mills theory. Okay, so how do we get the 0 plus 1D super Yang-Mills theory? As we said yesterday, we're supposed to consider the world volume theory of D0 branes, right? But now there's some non-trivial background, right? So in particular, let's discuss, so if you have some D0 branes, they couple this is how they couple to the fields that I've written here, right? So this is how they couple to the metric, the dilaton, and the Ramon background, right? So if we consider some gravitational wave, G could be slightly non-trivial, or we could consider, some wave which involves electromagnetism or this dilaton field. For simplicity, just because we don't want to work with tensors, let's consider a perturbation to the dilaton field. Okay, so now we have some scalar wave in flat space. Okay, so since we're working with linearized gravity, we can work out what the approximate effect of this perturbation is on the D0 brane theory itself. Okay, so what do? So we just take e to the phi and we perturb it by some amount, right? So, so this is the classical solution, which is just trivial. It's just a constant, right, in the original background. And now we put some field which may depend, let's say, on the transverse coordinates of the D brane, right? So this little phi could depend on t and also x, right? So what are these x's? These are the x's of the actual matrices, right? So the D0 branes, right, the D0 brane Lagrangian, the x's describe the actual location of the D0 brane, right? So depending on where the D0 brane sits, it might experience some source, 5x, right? So if we just Taylor series expand the interaction, right, we will get some things like this, right, schematically. This times the flat space answer. The flat space answer was basically trace f squared. Okay, so here we're considering a situation where G is still flat space, A is basically 0, but we have some non-trivial dilaton profile. Okay. Now, we have...
What is that answer for?
This, in the situation which I just said. Yeah. Now, let me be a little bit more careful, right? So what does exactly this expression mean? So first of all, X is a matrix. So this expression that I wrote in the front line only really makes sense for a single probe D0 brane. But let's try to make an educated guess about what would happen if we had non-abelian D0 branes, right? So we know that the action has to be UN invariant, right? So a UN invariant action would just be to put would just be to expand this field, right, in terms of x's. Sorry. I should have written something like this in the previous line, right? So here I've just expanded e to the phi, right? And we have some powers of x's. So a very simple guess for what the answer might be should be trace x1, xn up to f squared, right? So this now means matrix product, right? If when we have non-abelian matrices. And this is a very well-motivated guess for what, a collection of n D0 branes should feel in a weak dilaton background. Is that clear? Yes.
By n, like there's two different n's. There's the number of D0 branes and the n that we're summing over here, or?
Yes. I'm talking about the n by, okay. There's the capital N, so these x's are capital N by n matrices. And this trace means, trace over the n by n matrices. Maybe that's more clear.
Just to make sure I understand what's happening here. So before you were saying you're considering some graviton, like some linearized gravity.
Yeah, some graviton or let's say dilaton. It doesn't really matter.
I guess now we're talking about a dilaton fluctuation.
Yes, they're all in the same.
Can I view this as coming from like the 11D theory that's pure gravity, and then when? Yes, you could interpret it that way. Yes, the question was, can I interpret this dilaton as coming from the 11-dimensional theory as this R basically? And the answer is yes. But in the type 2A language, okay, we have some supergraviton multiplet. It includes all these bosonic fields and also their fermionic partners. I've, for simplicity, just focused on one component. Okay, so this is to give you a schematic argument for what happens to this theory now in the presence of some perturbation. Right? So the answer is simply that this super Yang-Mills theory gets deformed by something. Right? So I can draw it like this. Right? So what it gets deformed by is some term in the action, right? So we have SBFSS, the action of super Yang-Mills. It gets deformed by something, which is parameterized by some constants, right? Times this thing here, right? This is some operator. So this is some operator in the BFSS theory, right? So this thing here is some operator in the BFSS theory, and these are some parameters. We could call them lambda sub n of t. And we're summing. We're summing over n. So there are many different operators indexed by n, right? And that's related to the number of x's that appear, right? And they're related to what? They're related to the partial wave expansion of phi, right? So here we're essentially doing the partial wave expansion of this dilaton field, okay? So I've been a little bit schematic. There are many possible derivatives, right? So there's di1 up to din, right? These have some particular indices, right, corresponding to the particular directions you're considering. So in general, you get some deformation of the BFSS theory by some operators like this. Okay, so what have we learned? We've learned that from the super Yang-Mills point of view, this presence of this non-trivial background deforms the BFSS theory by some operators. What about from the gravity point of view? Okay, so from the gravity point of view, the picture that you should have in mind is that this dilaton wave in the decoupling limit, what does it do? It basically changes the boundary conditions that you should paste between the near horizon region and the flat space region. Right? So it's some wave that comes in, and it can change the behavior of some fields in the near horizon region, right? So from the DP brane point of view, we've changed the boundary conditions of the background near the boundary, right? And on the other hand, from the super Yang-Mills point of view, we've deformed the action by some operators. Okay, so that's the argument for the differentiate dictionary in general and gauge gravity duality. Here we just applied it to the zero brane case. Yes.
The way we arrived at the duality was via this double scaling limit, where we ultimately took G string to 0.
Yes, yes.
And now we're taking into account these interactions with the extra part. How did we do this before taking the limit or after? Like,
okay, excellent. Yeah, excellent. So the logic, yeah. Okay. One way to think about it is instead of working with flat space, we work with a background now, which has some wave. So then we're not focusing on the states that are right above the sort of vacuum state, which would be just given by n over G string over Ls. We're focusing on some states that are just slightly above that. And now we apply decoupling limit to those set of states. Okay. That's one way of thinking about it. Of course, if the, okay, so if this particle is extremely weak, right? So it's not particle, but the gravity wave itself is very weak. We can think of that as the leading interaction between a closed string mode out in the flat space region and the D0 brane theory. Both of them are legitimate ways to think about it. Yeah. Yes.
So I could apply this argument for the background for any fields in the supergravity split.
Yeah, in principle, you could try to change the argument to be some more non-trivial background, and you would derive other more non-trivial deformations of the matrix model. Yes. But in practice, this is a somewhat subtle business. I don't want to get into too many of the details, but yes. Yes.
Irrelevant deformations of
Irrelevant deformations of BFSS. I think at the level of the argument that I've given, it's not clear whether it applies to relevant or irrelevant. It's just a general argument about. I haven't yet told you about the dimensions of the object, for example. We can I think if you're not happy with this, we can discuss some more. Yeah. Okay. So let's now discuss. So this is the differentiate dictionary, right? We can use it to compute correlation functions, right? So let's discuss this in a little bit more detail. Okay. So in principle, we should look for solutions to the wave equation on this background. And in general, that sounds a little bit messy, right? This is some background. It seems like it might be a little bit tricky to understand what the correlation functions do on this background. But there's a simple trick, which is to relate it to ADS. So I thought I would spend just a few minutes on that. Okay. So the idea is the following, right? Let's consider, yeah, okay. Okay, let's consider the fluctuations. So this is the fluctuations of the dilaton on this particular background. Okay, so we can get this from the type 2 action, right? So there was some e to the minus phi and e to the minus 2 pi in the type 2a action, and expanding out in small parameters, and then using the equations of motion for type 2a, we can simplify the resulting action to just being something like this. But if you like, we can just view this as a starting point, right? So we have some dilaton, and it's coupled to some non-trivial, metric g, as well as some non-trivial dilaton profile, which is given by this solution here. Yes.
So are we looking for normalizable or non-normalizable solutions? Because here you are changing the BFSS action, so I would think it's a normalizable.
Yeah, let me continue for a little bit and then come back to that question. I think, yeah. Okay, so here we're just discussing the Lagrangian so far of the fields, right? So we're just considering the Lagrangian for one of these scalar fluctuations. And a very simple exercise is to work out what this is in the z coordinates. And what you will find is the following. So you will find something like this, dz, d tau, of course, z to some power. Okay. Okay, so what is this m squared? Right? M squared comes from expanding this phi in terms of spherical harmonics on the S8. Right? So we have some sphere. We consider spherical harmonics on the sphere. That gives us some equation for m squared. I think it's k plus 7, something like this. Okay. So these are the angular momentum modes on the sphere. These factors are kind of obvious, right? So we have z to some power. Some of the powers come from this expression for e to the phi, right? So there's some z to the 21. There's also some factors of z coming from here and here, right, when we compute square root of g. The overall thing gives you a factor of z to some power. And the observation is the following, right? This looks a lot like square root g ADS. Okay. Where square root of g ADS in Poincare coordinates also just gives you some power of z. The only funny thing is you have to choose ADS to be in a fractional number of dimensions, right? So since we got a fractional number of power, right, a lot of these things are not integers, so you probably get some fraction, right? When you get that fraction, you will need to use square root of g ADS for a fractional dimension ADS, right? So the d that you get in that computation is actually the same d that you get in this f factor here, okay? So d is like 14 over 5. Yes?
But the dimension of ADS also appears in the derivative.
Yes, 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 yes. And they all work out. They all work out. Yes, yeah. Yeah. Yeah, it's a little weird, right? So I presented this as some sort of empirical discovery. I would now, well, in a moment I will discuss the scaling argument for, it should be a little bit less mysterious. Okay,
But for now, let's just say, OK, this is some empirical fact that we observed with just calculating these trivial factors from the metric and the dilettante and so forth, right? So what do we learn from this? Well, the first thing that we learn is we can just import our knowledge from ADS-CFT, right? So in particular, if we have an ADS field with some mass, right, it has some conformal dimension. Delta times delta minus d is equal to m squared, right? Where d now is this fake d, right? So what does this mean? The conformal dimension means that the two-point functions are going to be like power laws, right? So we can immediately conclude, for example, that O is one of these operators, let's say. O of tau, O of 0, let's say at low temperatures, will go like 1 over tau to the 2 delta plus d minus 1. OK, you might be a little bit surprised. Why did I write some extra factor here and not just 2 delta, right, like in standard ADS-CFT? And the reason is the following. So we need to be a little bit more careful what we mean by square root of g ADS, right? So what we actually have in mind is that in ADS, we have a planar boundary, right? So the boundary is just flat Euclidean space in a fractional number of dimensions. If we like, we can take the extra fractional dimensions to be periodic. OK, so the extra dimensions have the topology of a torus, let's say. And then what we mean by these operators are not actually operators that are localized on the boundary, but they're integrated over those extra fake dimensions. Okay. When you integrate over those extra fake dimensions, you take a power law right on the boundary, you integrate it over the extra flat dimensions, you get some additional powers like this. Okay, so that explains why you don't get exactly tau to the 2 delta, but you shift the exponent by a little bit. I'll give another argument in a moment. OK, so this is great. So in particular, we can actually calculate what delta is, right? So for this particularly simple perturbation, I've actually calculated it basically from gravity. So you also have to keep track of factors of RADS. So RADS is not 1 in these conventions, it's like 2/5. So that introduces some factors of further factors. But just basically using this equation and the fact that the spherical Laplacian has these eigenvalues, you can actually calculate the dimensions of many of these operators, right? And once you know some of the dimensions of the operators, many of the other dimensions for related operators follow by supersymmetry. So for example, you can use the fact that this operator, so this operator f, right? F is basically like the second time derivative. You should think of f as being like x dot, right? So this is basically like you can think of this as the commutator of q with x, and then the anti-commutator again with q with x, right? So 2q's is like a Hamiltonian, which is like a time derivative. Okay, so the point of this is you can actually derive the dimensions, for example, of the operator with no f insertion, just because it's related by supersymmetry to this particular operator. Okay, so in particular, you can derive the dimensions of pretty much all the supergravity modes via this kind of simple argument plus supersymmetry. Okay. So what we've learned is not just well, we've talked about the thermodynamics of the type 2a black hole, but we've also learned how to compute correlators in this background. So this is all like, you could say, very similar to ADS-CFT 101, but just applied to the zero brane context. The great thing is, since you're all somewhat familiar with ADS-CFT, you can apply your knowledge to trying to understand this problem to some degree. Yes?
So the two-point function argument, I would buy it for like a CFT, but
yes.
Here we also have the other scale in BFSS, right?
OK, so the argument that I gave was purely from the bulk. Right? It was only about analyzing the bulk Lagrangian and noting that it was similar to ADS. So when we make that argument, we're then using the fact that that in ADS-CFT, we can compute also the correlators directly from the bulk without referring to the CFT, and we can get the two-point function that way.
So some CFT unrelated to BFSS.
I'm not exactly sure what the question is, maybe.
I can answer it.
Yeah, so I will point out one caveat. So one caveat is this argument is special to supergravity modes. So it does not apply to, for example, massive stringy modes. If you work out the action for a massive stringy mode, it will not have this nice form. Okay, it will not look like a massive field in ADS. And that part in particular means that the correlators in BFSS for massive stringy modes does not have this simple form. Okay. Okay, I want to just try to demystify this argument a little bit more. So, so this stuff actually follows from a scaling symmetry argument. It was discussed in some older papers and also in a recent paper by Juan and Anna Biggs. Okay, so the scaling symmetry is extremely simple. You just take t goes to gamma t, z goes to gamma z. You hold n fixed and g squared fixed when you take the scaling symmetry. And that acts on the metric, the Ramon gauge field, and the dilaton, and changes the solution, right? So you get a new quote unquote solution. It's not actually a solution. Well, okay, sorry. You have a particular configuration. Okay. You have a particular configuration which is given by these expressions. You apply that scaling symmetry, and you get a new configuration. Okay. You can check, is the action invariant under this quote unquote symmetry, this transformation? It is not invariant under that transformation, but the next best thing happens. Okay. The next best thing is that the action just changes simply. So the action changes by some gamma to some power. Okay, I believe it's minus 9/5. This number here is related to the d, shifting it by 1. Okay, so the action, so this is not really a symmetry in the standard sense, right? The action is not left invariant under this transformation, but since the action changes very simply, it's still very useful. Okay, so in particular, if you want to compute the thermodynamics of the solution, knowing the scaling symmetry basically immediately gives you how the entropy scales with the temperature, for example, or how the free energy scales with the temperature. Because acting with T will transform beta. You can think of, right, beta is basically like T, right, in Euclidean signature. So scaling beta will scale the action. The action is like the free energy. You know how the free energy now behaves as a function of beta. Okay, so you get some, you can recover the thermodynamics simply from, once you calculate this exponent, you can easily get the thermodynamics. Okay. What else is it good for? Well, it's actually good for explaining some features about this kind of argument. Okay. So let's recall something simple. So let's recall something simple. So first of all, the boundary conditions in ADS, how do they work? Right? So if we have some scalar field chi, right, as it approaches the boundary, so as z goes to 0, as z goes to 0, chi goes like z to some power, right? And the coefficient multiplying z is what we call the boundary condition, the renormalized value of chi, right? So this could in principle depend on the boundary time tau. Okay, so here we're imagining solving the wave equation for some wiggly, let's say, boundary condition near the boundary. And then we solve it radially inward with these initial conditions. Okay. So we already said that there's a scaling symmetry, though, right? Where z goes like gamma z, right? So this just means that we can think of this equivalently as acting on this. If we had a solution to the bulk equations, this symmetry would simply send chi r goes to chi r times gamma to some delta, right? Because of this simple factor here. Okay, now let's think about the action, right? The action in the quadratic approximation, in the free approximation, right, is just quadratic in this boundary condition, right? So we're calculating the action when you deform the boundary conditions a little bit, right? So in the quadratic approximation, you're going to get an action that is proportional to just what? Chi r of u, sorry, chi r of tau, chi r of tau prime, g of tau minus tau prime, right? You're all familiar with this in ADS, or should I explain a little bit more? Okay, so in the differentiate dictionary, right, we said that when you introduce a perturbation, you change the boundary conditions, right? Then if you want, you can consider differentiating with respect to that source, right? So you can think of this chi r of u as what I called lambda of t in this equation here, right? When you differentiate with respect to this, you bring down one of these O's, right? You bring it down from the action, and you insert it. It becomes a correlator. So if you bring down two of these guys, you get the 2-point function on the boundary, g of tau, right? Now, this s goes to gamma to the minus 9/5 s will then immediately tell you what g is, right? Because chi transforms like gamma to the delta, right? So you get something like, under a transformation, this will give you some function like gamma to the 2 delta. And and demanding that the overall action also scales non-trivially like gamma to the minus 9/5 will fix how g scales. So g will then scale like 1 over tau to the 2 delta, and then some additional factor, which was this d plus 1 thing, or d minus 1 thing that we discussed in the previous case. Okay, so this scaling symmetry will completely fix the form of the correlator. Okay, yes? Okay, so the SO9 symmetry is related to this number k, right? So what we've done is we've expanded the spherical harmonics. So we have the horizon. Here's the horizon of the black hole, right? We have some, spherical harmonics on this horizon. These are some particular modes, right? And what we've argued is that some particular operator which carries angular momentum, right? So an operator with a bunch of x's like this will carry some angular momentum because these are indices which carry SO9 angular momentum. So what we've argued is that some operator which carries SO9 momentum in the gravity picture will correspond to some particular deformation of the geometry or of some fields in the geometry that is not invariant under SO9. But maybe you're asking about this because there's no picture like in ADS where you can think of points on the boundary, on the boundary sphere, for example, as corresponding to some points in the bulk. We don't have a direct picture like that. Yes?
Why is chi r related to this lambda?
So chi r is the boundary condition for the bulk field, right? So chi r, when z goes to 0, we're going to the boundary, right? So we have some ADS boundary, right? We're approaching z equals 0 here, right? And we have some fields, right? The fields have some power law dependence on z. And what we call the boundary condition is really this, right? Chi r. Okay. The point is that from the decoupling argument, that change in boundary condition is related to deforming the Super-Yang-Mills action by some particular operator. How much do you deform by the operator is proportional to the change in the boundary conditions. So this lambda thing here is just chi. That comes from the picture that we drew on the left-hand side, right? So if you have a very strong amplitude, right, then you will deform the Super-Yang-Mills theory by a lot. You'll perturb the Super-Yang-Mills theory by a lot, and that will also change the boundary conditions by a lot, sort of in the decoupling region. That's the heuristic picture you should have in mind. Okay, so now let's discuss the, yeah, okay.
For this chi to change boundary condition, does delta need to be negative? Because otherwise, error.
Yeah, so this is the renormalized value of the field, right? So this is related to holographic renormalization. So technically speaking, these fields could be going to 0 for positive delta. But we defined some renormalized field which is held fixed in the limit. Yeah. Yes?
Did you also take some boundary condition and z equals infinity, or because that background is a bit singular? So
yes, thanks. Yes, thanks. I was actually about to comment a little bit on that. Okay, so what exactly are we talking about when we neglect this f factor here, right? So this geometry, it looks like it looks a bit like Poincaré ADS, but there's some funny features, right, at z very large, right? And in particular, let's focus on this this equation, right? So z, as it gets very large, you see, okay, each of the phi is the effective coupling of this theory. In order to trust the tree-level approximation, we need the coupling to be very tiny, right? So it's tiny because it's suppressed by 1 over n, and we're assuming that n is very large, okay? However, if z is starting to scale like some powers of n, right, the coupling is no longer small, and we need to uplift to the M-theory discussion, right? So we can uplift to this black string discussion that we had yesterday, right? So that was some 11-dimensional solution. But if we're truly at 0 temperature, that's actually not the correct solution, depending on how you scale t with powers of n, right? So in particular, as one of the homework assignments, you were supposed to argue that if the temperature is super small, there's a Gregory-Laflamme stability of this black string, and you actually visualize an 11-dimensional black hole. Okay. So that's the most appropriate description. So in principle, we need to worry about that. But from the point of view of the correlators, as long as we're computing correlators for times that are not super large, right? So there's various time scales. There's beta, the actual time scale of the actual temperature of the black hole, but there's also the separation, tau, right, which governs the 2-point function. If tau, for example, is in the 't Hooft regime, we can use this geometry reliably. Okay, and that's simply because the correlators do not really probe into that deep region. So maybe I'll draw one more picture, which will be helpful. So this is like Poincaré ADS, right? We have some slices. The dilaton is growing in this direction. The dilaton gets very big here. So we have some sort of 11D uplift near here, right? But as long as we compute, let's say, correlators that are relatively, are separated in times that are, let's say, within the 't Hooft regime, we never really probe that sort of bad area, bad or good, depending on your point of view. We never probe that area, so we can use the 10-dimensional metric that we wrote down to do that computation. Okay, this picture will also be slightly useful in what I'm about to say. Okay, so let's now discuss scattering. Okay, so yeah.
Can you remind me why we ignore the F factors over there?
We did not. We could either work at finite temperature or 0 temperature. Yeah. So in general, at finite temperature, we should have these factors. Yeah. Yeah. Next slide. Yeah. Okay. So let's now discuss another variation of the decoupling argument. Okay. So this is going to be related to scattering, and the idea is the following. So instead of having n d0 branes just at some point in space-time, we're now going to consider a situation where we put n d0 branes at different points at space-time, right? So we could have some d0 branes here, n1 here, and let's say n2 at some other point. Okay. So this is described by some, R1 and R2. And, well, you might worry that these objects will either attract or repel. But because they're BPS, the attraction due to gravity exactly cancels the repulsion due to electromagnetism, right? So these are d0 branes. If they were d0 and anti-d0, you would worry about this situation. But since they're both d0, the repulsion from the ENM exactly cancels the gravity. And you can put them anywhere. So there's a moduli space of where you can put them. Okay. So what is a description of this? There are several ways to think about it. One way is, again, from the bulk point of view. So recall we had this function, 1 plus 1 over n r to the 7, L string to the 7. GS. This was roughly the warp factor that we had yesterday, right, for a single d0 brane. The very natural generalization is just to replace this with a harmonic function. Okay. So, yeah, maybe I should. Let me just get the factors right. Okay, so the harmonic function, you basically put this here and put, you could call this factor here ni, basically. Yeah, let me not try to, I was going to write down the order 1 factor, but I don't think it'll be important for the discussion. So it's a very simple generalization of the geometry that we discussed yesterday. And what does it look like? Well, yesterday we drew some picture like this, right? So there was some flat space region and then some near horizon region. Now we have sort of multiple of these guys, right? So here could be one with n1. So there's a d0 brane charge that's n1 associated with this throat, and some n2 associated with that throat. Okay. Yes, thanks very much. Yeah. Oh, sorry, the sun goes here. Thanks. So this is actually a solution to the supergravity equations. Okay. Okay, so this is a picture where we have multiple extremal black holes, right, located at different locations, and they all have these long throats. Okay. And what is the description in terms of the D0 brains, right? Well, in terms of the D0 brains, we need to discuss a little bit more about what the boundary theory actually is. Okay, so let's do that. Okay, so you should hold this in mind. We're now trying to discuss what the states are in the D0 brane quantum mechanics that gives you this description. Okay, so the D0 brane quantum mechanics has some terms, right? The trace goes in front of this. We also have some fermions. So we have some fermions. Right, so we have a gamma matrix which has SO9 index I. It's contracted here, and these guys are spinors. So the fermions are spinors of SO9. Okay, so they have the correct index contraction pattern so that this whole interaction is SO9 invariant. Right? Yes.
So because these guys are BS, I can have these throats be as close as I want.
Yes.
Issues or?
Yes. Yes. Let's hold that thought. Yeah. Let's hold that thought. Okay. So. Okay. So let's discuss what we think we know about the D0 brane quantum mechanics, just from the point of view of the boundary. Okay. So from the point of view of the boundary, what do we know? So let's keep n finite for now. So the energy spectrum is supposed to look like this. So E equals 0 is here. Okay, this model has 16 supersymmetries. Okay, so yeah, so this equation implies that the energy has to be positive, right? So we definitely don't have any states below energy equals 0. What's conjectured is that there's exactly one state which has E equals 0. And that is a bound state. So it is a normalizable bound state. Normalizable means, it's not a scattering state. You can integrate psi squared, basically, and get 1. Right? So there's a normalizable bound state here. And then there's supposed to be a continuum of scattering states at finite energies. And the continuum is supposed to extend all the way to E equals 0. There's no gap between the continuum states and the E equals 0 state. Okay, so yeah. Yeah, you could do that. Yeah, it's actually yeah. Okay. Yeah. Okay. So we can consider a scattering state. What is the form of the scattering state? Okay, so here's the conjecture for what the scattering states look like. Okay, so you take the X matrices, and you do something like this. So they look kind of like this. They're block diagonalizable in the scattering states. Okay, and these blocks here are now described by some wave function. So here in the off-diagonal blocks in some particular gauge, they're exactly 0. So the wave function is localized at all of these components being 0. Okay. What is the wave function in these blocks? The idea is that you put psi of the normalizable bound state of a smaller BFSS. So here's n1 times n1 BFSS. So this is some function of x, and you put it in here. Okay. And in this block, you put psi n2 by n2. Right. So you put the ground state of a different, smaller BFSS model into these blocks. Okay. Now, I still haven't told you the full story. So first ingredient is the normalizable bound state. But then there's one additional ingredient. Right? The additional ingredient is the center of mass mode which we call little x. So recall in Yang-Mills theory, if you have a UN Yang-Mills theory, right, the U1 factor decouples, right? The U1 factor is the location of the zero mode of the D0 branes, right? It tells you where you are. And that factor is kind of trivial, okay? So it's trivial in the sense that it's just free. It doesn't participate in these interactions, right? Okay? And it's just described by a single coordinate. So it's just described basically by a free particle. H is equal to p squared over 2. Okay, it's just this is the center of mass mode, okay? So we know what the scattering states of this Hamiltonian are, right? They're just plane waves. So the full answer is you take the blocks which have some center of mass, which we call little x, and we put them in a scattering state e to the I px. Okay, does that make sense? So what are the parameters of the scattering state? We have basically n, so n1, the size of a particular block, right? And associated with each block is also a momentum, p, right? And so we characterize the scattering states by some ni's and pi's. And the energy of the scattering state is just the sum of the pi's squared weighted by the factors of ni, right? So weighted by the factors of ni. So that's the conjecture for what the scattering states look like in BFSS. So that's the conjecture for what the full spectrum actually looks like. Well, I've only told you asymptotically what these states look like. So I'm describing the ingoing states, let's say, of BFSS. Of course, what happens is these are some wave packets. They come in, right? They scatter. And they do some horribly complicated thing when they're interacting. We don't know how to describe that, right? In principle, we would like to understand that better. But what I'm just telling you is asymptotically what they look like. So now you might see that there is a relation to the previous slide, which is covered up, right? So previously we had these ND0 branes, right? We also had N1, right? Related to the the charge of each of the D0 brane black holes that we had at different locations. And they also had some positions that we could call Ri, right? The Ri's have some conjugate momentum, right? So there's a clear relation now between these scattering states and those states that I discussed above in the 't Hooft limit. So let me try to be a little bit more concrete about that. Yes?
So each of the D0 brane black holes comprise more than one. They are like in a bound state.
Yes.
But you were saying because they're BPS, so there's no interactions?
Yeah, there's no, asymptotically there are no interactions.
Oh.
So what does that mean? Okay. We're about to discuss this, so thanks for the question. Okay, so from the boundary point of view, what is known, there are some index arguments. I think they're most solid in n equals 2, but there's been a general index argument for why the number of bound states is at least 1. Okay. The index does not tell you whether there's a, the index being 1 does not tell you that there's more. Yeah, okay. Yeah, so that's one piece of evidence for this conjecture. It's a very subtle argument because the flat directions. So it's not the standard index argument. It's a somewhat complicated index argument. The fact, I actually do not know if other aspects of this spectrum have been thoroughly checked. For example, could there be another bound state somewhere in here? That would violate actually the BFSS conjecture, I think. We can discuss exactly why. But I do not know if, from the boundary side, if there's been any rigorous argument that rules out the existence of some finite energy bound states. I could be wrong about this. I simply don't know. Okay. Yes.
The original BFSS Hamiltonian that you wrote up top
Yes.
came from this decoupling argument with a single stack of D0 branes.
Yes.
And now you're saying that within this Hamiltonian, we can find also many different stacks of D0 branes.
Yes.
But this came from just one. So
Yes. 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 So what we should do is we should rerun the decoupling argument for this particular setup where we now have, instead of the simple H that I wrote down, that more complicated H, and also follow what happens on the super Yang-Mills side. And from the Super-Yang-Mills side, in the decoupling limit, we basically give vebs to the particular locations of the D0 branes. We do this block diagonal thing, basically.
Perfect.
Yeah. OK, so let me discuss the gravity solution in a little bit more detail. So I just told you the setup where we have n D0, n extreme, sorry. There's too many different n's. So we have a collection of black holes, right, at various different locations, and they're all static in the solution that I just wrote down. Okay, they're not moving with respect to each other. We can generalize this a little bit to make the black holes move slightly with respect to each other. So they have low velocities. Okay, so how do we do that? Well, it's basically, I just wanted to mention this because it's a little bit fun. It's basically post-Newtonian approximation. So it's very similar, actually, to what some people at LIGO do, except for a slightly exotic theory of gravity. Right. So. Now I'm going to bend upwards. OK, this was basically the solution that we wrote down yesterday, except now, sorry. This was basically the solution that we wrote down yesterday, except we put a slightly more general h of r, right? Now, to further generalize this to the case where it's moving, we do some very simple things. So we had these ri's. We now make them functions of time, right? So here was r1, and here was r2. And now these vectors could depend on time a little bit, okay? That's one thing that we do. We also have to add an off-diagonal component to the metric. We basically have to do this in order to satisfy the constraints of general relativity. Okay, but yeah, with this very small modification of this metric at low velocities, we can actually check that this again satisfies the Einstein equations. Okay, so what does this tell us? Well, there's some solution which is nearly BPS, right? It's nearly BPS in the sense that we have this very low energy solution where the black holes are moving very slowly with respect to each other. Okay. And what is known about the solution? So the idea is that you plug this metric into the action. Okay, you plug it into the type 2a action, and you expand in small velocities. So you only keep terms up to, let's say, velocity squared. Okay, in the action. What do you find? Well, the question is, what is it as a function of r? Right. So the answer, well, on general grounds, the Lagrangian that you could recover as a function of, let's say, r1 and r2 should look like this, right? It should be some potential that's a function of r, where r is like r1 minus r2. Right? This is just from rotational invariance. Okay? We could also have a term like g of r v squared, right? Maybe with a 1/2. And we could also have higher order terms. Okay? What you find when you actually do this computation, and this computation was done in an old paper by Shirashi, is that this term actually vanishes, and this term is just equal to 1. Okay, so this term vanishing is just the consequence of supersymmetry, as I've been saying, right? It says that there's no potential, there's no static potential between these black holes. Okay, this follows, but you should, yeah, okay. This follows just from the cancellation of electric and gravitational forces. This thing is also a consequence of supersymmetry, but it's more subtle. It says that the metric on moduli space of the solution is just trivial. It's just a trivial metric. Okay, so supersymmetry actually is also playing a role in setting this equal to 1. I think I won't detail this, and I won't explain this in any detail. Okay, now so the most interesting contribution that you could get that would be kind of non-trivial would be the v to the 4 term. Okay, so there will be some v to the 4 term, and it could have some f of r dependence in principle. Unfortunately, Shirashi did not compute that. And in order to compute it, I think in principle, you could go to higher orders in this post-Newtonian approximation, right? It's Newtonian because these things are moving very slowly with respect to each other and so forth. As far as I know, this has not been done. So if anyone wants to do this, this is like a challenge problem. I think it's much more non-trivial than the homework exercises, but I think it would be a cool thing to do. Okay, but I will now give an indirect argument for what this term actually is. Okay, so what's the indirect argument? Well, the idea is the following. So now maybe I'll use my other board. No. Okay. So the idea is that we're going to now consider a further limit where n1 is much smaller than n2. So in order to justify this supergravity approximation, as before, we had to take both n1 and n2 very big. But we can consider now a regime where n1 is super big, but n2 is not that big. That's another possible regime that we could consider. Okay? Then we have a slightly different description of the physics. What is the description? Well, you might be able to guess it. So, unfortunately, so we had this diagram, and the description could be, here's the background created by, let's say, n1. So n1 is much bigger than 1. We have just a single extremal black hole. And then n2 is very small. So what could n2 be? So it could be a cluster of d0 branes that travels in this geometry. Right? So if n2 is much smaller than n1, we could try an approximation like this. So this means that we use the probe dBi action. Okay? We use the probe dBi action in the original background of the n1 d0 branes. Is that clear? Yes, no, yes. Okay. So the probe d0 dBi action we've written down now several times, right? Let's write it down one more time. Okay, so we just work out the probe dBi action in terms of one of these coordinates. And I'll spare you the details. It's just a matter of plugging in the solution, right? When you plug in the solution, you get something very nice. You get this expression, okay? I think that should be plausible from the form of the metric that I wrote here. Yeah, I should mention one thing. When I said that x's correspond to the location of the d0 branes, I was implicitly saying that the x's correspond to the r's. Right? You could ask which coordinate system is relevant. Is it the z's or the rho's? When you talk about the translation between x, it's most directly related to r. And you can see that from various points of view. We could discuss this a bit afterwards. Okay. So we're now writing the action of a probe d0 brane in these coordinates. We also have a factor of n, multiplying out front. So this n was actually n1. So this is for a single probe d0 brane. If we had multiple of them, well, some kind of approximation would just be to multiply by n2, right? So this action would govern the trajectory of this particle. And one thing that you can check is that there actually are trajectories that do this. So they start sort of asymptotically at infinity. They come in, define a radius, and then they go back, right? So here v is not just the radial. So v is rho dot squared plus the angular piece. It's the full velocity in 10 dimensions, not just the radial direction. Okay, so let's now just expand this action at small rho. At small v, right? So at small v, the cool thing is, first of all, this term here cancels this term. What was this term? This was coming from A0, right? So this is saying that gravity cancels electromagnetism, right? So we get, to leading order, we get 0. Then we can expand to quadratic order, right? So there's also a minus sign in front of this action. So this was the dBi action. Okay. To leading order, we actually get this. So there's also factor n1, n2 here. Okay, but the point is that there's no rho dependence, right? So that's, again, recovering this statement here. And finally, we can work out the higher order terms, of course. So there will be a v to the 4 term. There will also be a v to the 6 term. And we get some rho to some various powers. Probably 7 here. And probably, who wants to help me out? 14. Very good. OK, and of course, higher terms with some particular coefficients, right? Now, it's an exercise. Convert. So these were the v's and rhos. Convert. Go all the way back. Convert it into r, right? Convert everything back to r. This r, right? Using this equation. And also convert it back into the M-theory parameters using these equations. Okay, so write down the potential in terms of that. And then you will see these famous factors appearing. So in particular, what am I talking about? So you can actually do a matrix model computation. You can actually do a matrix model computation just by doing perturbation theory and super Yang-Mills. And when you do perturbation theory and super Yang-Mills, people famously worked out, already in the first BFSS paper, they found this structure. So they found no term here due to supersymmetry, no term here, well, just a trivial term here, and some v to the 4 over r to the 7 term with some particular coefficient. And if you work out the whole conversion factors, you will find that we just derived from the bulk point of view what that coefficient should be. Okay, and the particular fact that it's r to the 7 and not something more complicated. Okay, so this was a loop expansion actually in the matrix model. So this was a one loop. So from the matrix model point of view, this is a one loop term. This would be like a two loop term, et cetera. Okay, so maybe before I was going to spend maybe 2 or 3 minutes just explaining that. But before I do that, is it clear what the claim is? Yes.
So on the right-hand side, this is like saying the two blocks and the BFSS, like they would correspond to the two black holes on the left-hand side, that the crosses here. But
Yes,
from
yes.
the picture that you drew, that would be you have like two throats.
Yes, yes, exactly.
How do you see that the block should correspond to the throat?
How do I see that the blocks? Okay, so the idea is that each block is like a cluster of d0 branes itself. So it's described by a wave function, which is basically the ground state wave function of BFSS. And that, just for that block, the ground state wave function of BFSS from the decoupling arguments should be some extremal geometry. Then the other block should also be some extremal geometry. Now you could wonder about the off-diagonal modes, and we'll discuss that in 1 second.
So is this v to the 4 over rho to the 7 protected in any way, or
Is this what protected?
Is it protected, or is it like completely like something like this?
Yeah, the question was whether this calculation is protected. Right. So the answer is yes. In principle, okay, I haven't discussed, I'm getting a little bit ahead of myself, but in principle, there could be infinitely many corrections to the v to the 4 term, just the v to the 4 term. So in particular, you could imagine there's a whole series here that's a function of 1 over rho to some power. Okay, like this is just the first term, and then there's the corrections. Those would all violate the BFSS conjecture, right? Thankfully, they do not appear, and they do not appear because of supersymmetry. So there's some non-renormalization argument that says that all these terms are 0.
But since we work at finite and then at the next order, these will probably appear and the BFSS will get violated. Because we are probing like this singularity at infinity, and it's a bit like sig here, it's like a large impact parameter. I would think this is like a BPS accident.
I'm not exactly sure what the question is. Maybe we can discuss it, yeah. Yeah, you could wonder that the existing tests use BPS in a very strong way, and it would be nice to have some non-BPS tests of the conjecture. I think that's a reasonable goal. But I think all the tests that have been done are consistent with, with this answer, yes.
We discussed this later, but I think the question was about how starting at the v to the 8 term, you don't get like the series starting at the v to the 8 term doesn't just go to 0.
Yeah, let's just focus on the v to the 4 term for now. Yeah, okay. So how much time do I have?
About 6 minutes.
Okay, 6 minutes. let me just do two more little things. So first of all, I should say that this computation should approach this computation here, where we did a computation involving black holes versus a computation in the DBI action, right? When we, roughly speaking, we think of the second one as a very tiny sort of extremal black hole, right? Moving, now this thing will be moving on the background of this big N1, much bigger than 1 geometry. Okay, so these two calculations should agree, but as far as I know, no one has done the actual GR computation. That's one comment. Another comment is the following. So let's discuss the loop. Well, actually, maybe instead of discussing the loop computation in BFSS, maybe I'll just spend the remaining time to just stating what the BFSS conjecture is. Okay, so the BFSS conjecture is about the scattering amplitudes. Okay, so what are the scattering amplitudes in this theory? So they're a function of the particular parameters that we discussed, right? So we have P1, N1, P2, N2, etc., right? These are the scattering states that we just discussed with blocks and so forth, where the center of mass of each block was conjugate to these P's, right? So this is the scattering amplitude in quantum mechanics. And the idea is that in BFSS, the BFSS conjecture is that this is directly related to the M theory parameter, the M theory scattering amplitude. So this is an 11-dimensional scattering amplitude in flat space. Flat space uncompactified. So just to emphasize that, uncompactified. Okay. Now, in order to relate the two amplitudes, we have to furthermore take some limits. So we have to take the large N limit. So we take limit n goes to infinity, and we also take r goes to infinity. So if you like, r was some dimensionful scale, right? And we're supposed to convert g squared Yang-Mills in terms of r using these equations, right? So what it ends up saying is that we take a very low energy limit. So any energies that we consider in the BFS model are very low energies, and n goes to infinity. Okay, and from the geometrical considerations, you can already anticipate that this limit is such that we're beyond the 't Hooft limit, right? So the 't Hooft limit was like fixed temperatures, fixed energies which probe the type 2a region. In order to get to the M theory limit, we need to take the 't Hooft parameter to scale with some n to some power. Okay, so that means we're going to an ultra strong coupling limit of the matrix model. Okay, but let me just state the conjecture. So the 11-dimensional scattering amplitude is, of course, a function of, well, these pi's, right? But also one additional p plus and p minus, right? So p minus you can think of as just n over r, holding these quantities fixed, right? So we're taking all of the ni's to infinity, r to infinity, in such a way that p minus is being held fixed. Okay, so this defines some p minus. What do you get? How do you get p plus? Well, you get p plus by solving the mass shell condition. So these are massless objects in 11 dimensions, right? These are the only sort of asymptotic states in M theory. In asymptotically flat space in M theory are the supergraviton multiplets. So these are massless objects, and they satisfy the mass shell condition. So these are how the M theory parameters p plus, p minus, and pi are related to the matrix model parameters. Okay.
P vector squared in the mass shell condition?
Yes, thanks. P vector squared, thanks. Okay, so if you like, we can write this as p mu 1 to however many blocks we have, right? And the amplitude here is just literally equal to this up to some factors of 2 pi and r. So these are just some kinematic factors that are not so important. Here, n is the number of p's, the number of blocks. Okay. So this is not a very important factor. The main thing is that these two amplitudes are literally equal to each other up to some proportionality factor. Okay. So what is the intuitive picture? I think maybe we can discuss this a little bit more now. So the intuitive picture is we send this, let's take a case where N2 is very large, and N1 is very large, and we use this D0 brane picture. So we think of N1 being much bigger than N2. We have some geometry that looks like this. So asymptotically, what we're doing is we're sending in some particle into the geometry, right? If we work at fixed energies in 't Hooft units, this particle just stays out here. But if we go to ultra low energies, this particle can get very, very close to the sort of horizon, right? And this is the region where the coupling becomes very big, right? Where, according to that equation, we had this equation where the dilaton goes like z to the 21/10, right? So for very low energies, this factor can become large, and we're basically isolating some sort of scattering that happens in this 11-dimensional bubble. And if the 11-dimensional bubble is big enough, then we should just get the flat space answer. That's roughly the intuition from the modern viewpoint. Okay, we first send something in. It first goes into this terrible region. Okay, this terrible region, why is it terrible? Recall that this was a singular region from the boundary point of view, right? The size of the sphere was below the string scale, and there's all sorts of stuff that happens, right? So there's this type 2A region, which in principle is a little bit stringy. You start a D0 brane from that stringy region. It goes into this, it goes through this 10-dimensional region. It finally ends up in some sort of 11-dimensional flat space region. So that's quite surprising then from this point of view that you would have a direct equality, that you don't have some additional factor in this equation that accounts for some of all this sort of non-trivial stuff that we just discussed, right? In the original conjecture, it was just about 11-dimensional flat space. They never had to talk about this non-trivial black hole background. Okay, so why is that factor supposed to be basically 1? Okay, the argument is both from the gravity point of view, when you look at this Lagrangian, and from the matrix model point of view, these functions are basically trivial in the large r distance, right? So we analyzed this in the type 2A regime, and we found also that this potential is basically trivial at large r, right? Both the moduli space metric and this thing here is basically just either 1 or 0, right? So that means that when you go to very large r, sort of nothing interesting happens. The only thing that happens is free motion on a moduli space. And similarly, from the matrix model point of view, we haven't quite outlined the loop computation. But if we're going at very low energies, we should be able to trust this kind of effective potential at very low velocities. And that effective potential basically had no interesting interaction. It just had a free particle motion. Okay. So the idea is that even though the type 2A geometry could in principle get complicated and stringy, somehow we know from the matrix model side, I would say, yeah, and also it's hinted at just from this naive computation that sort of nothing interesting happens. So this should be contrasted a little bit with how you might try to take the flat space limit of ADS-CFT, right? So in ADS-CFT, you can try to imagine scattering some objects into the bulk in ADS, right? And then you would have some bulk to boundary propagator in ADS, right? And you would have to account for this bulk to boundary propagator in order to properly extract the S matrix, the flat space S matrix. Here, we do not have that issue. Somehow the quote-unquote bulk to boundary propagator is just trivial, it's just 1. Another comment is in ADS-CFT, right? Okay. One more sentence then. In ADS-CFT, when we scatter, okay. When we scatter, we think of these as objects that are moving in some space-time that is sort of dual to the full CFT, where in this picture, the actual matrix, the block diagonal matrix, is itself creating its own space-time. And that's how the scattering happens. So the picture of how the 11-dimensional sort of physics emerges is quite different between the ADS case and the BFSS case. That's the only comment. All right, thanks a lot.